So we illustrate another type of bifurcation called a Pitchfork bifurcation. And as usual, we identify that this is f of x u. And we need to find the equilibrium points. So in this case, we are going to set f of x mu, which is equals to mu x. So I can take x outside, mu minus 4x squared is equal to 0. And again, in this case, x is equal to 0 is one of them. Let me call it x1. And then I of x is equal to plus or minus the square root of mu over 4. That's one, which is equal to plus or minus 1 over 2 times root u. And again here, because we're dealing with the square root, we need to take care of real valued solutions here. So we have now x1 is equal to 0, x2 is equal to half root u, and x3 is equals to minus half root u. Now, provided for these two, mu is greater than 0 for us to have distinct roots, but remember mu is equal to 0 is also a possibility, which will unfold when we now deal with the stability of the equilibrium points. So we have 3 equilibrium points for a Pitchfork bifurcation. And it is important to also note that x1, 0 exists for mu. X1 is equal to 0 for mu is between minus infinity and infinity. But x2 and x3 that are equal to plus or minus half root of u, they only exist it is this for mu between 0 and infinity. So even when we draw the bifurcation diagram, we need to take care of these different domains of existence of the 3. Okay, so as usual, we then test for stability by differentiating f of xy with respect to x. So this will give us mu minus this is 12x squared. That's our derivative. So now let's start evaluating at the equilibrium points. So this then says that the derivative is equal to mu, and we check the conditions for stability of the equilibrium point x1. So if mu is less than 0, mu is greater than 0, or mu equal to 0. And then we basically see that this is stable, unstable, and non-hyperbolic. And this means, in this case, x1 is equal to x2 is equal to x3. That's what it means. Okay, let's also try to test first. Okay, let's conclude first. So x1 is equal to 0 is stable when 2 is less than 0, unstable when u is greater than 0, and non-hyperbolic when u is equal to 0, where we claim that at that point we observe that x1 is equals to x2 is equals to x3. All the equilibrium points meet there at the point when u is equal to 0. Okay, let's try to check for stability of x2, which is equal to mu minus 12 times the half times the square root of mu. Half times the square root of mu squared. This is mu minus 12 over 4 times mu. So that's mu minus 3 mu, which is minus 2 mu. But remember, for existence, u should be greater than 0. So then, okay, let me write it here, which is equals to mu minus 3 mu minus 2 mu. But this is less than 0 since for existence of x2, u should be restricted to greater than 0. So we don't need, there is no need to check when u is less than 0. Why? Because it doesn't exist as a real valued equilibrium when u is less than 0. But we also just know as well that is equal to 0. So we are here, this is equal to 0 if u is equal to 0. So we only have two cases for the equilibrium x2. So x2 is stable when u is greater than 0. And non-hyperbolic when it's equal to 0. Yes, then we can't talk about mu is less than 0. So it's either stable or non-hyperbolic. Let's also check with x3, stability of x3. It's u minus 12 times minus half root u squared, which is just u minus 3 u, which was minus 2 mu, which is also less than 0. Less than 0. This is less than 0 when u is less than 0. Right? When u is less than 0 and equal to 0 when u is equal to 0. And we don't talk of greater than 0 because it doesn't exist today. So also we can easily conclude that x3 is stable when u is greater than 0 and non-hyperbolic when u equals 0. So we now can observe that there is a bifurcation point. So there is a bifurcation point. There is a bifurcation point at 2 equals 0 and x there is actually x1 is equals to x2 is equals to x3, which is just the x star or IU is equal to 0. So the bifurcation point, let me just call it uh, um, U naught X naught, where X naught is X star is actually equal to 0, 0. So all the 3 points meet at 0, 0. So now we have to then draw the bifurcation diagram. And how do we draw the bifurcation diagram? We have to plot X equal to 0. We have to plot X is equal to 0. So let's plot X is equal to 0 when U is an element of minus infinity to infinity. And then X1 is equals to half root mu when U is greater than or equal to 0, or if you want, is an element of 0 to infinity. And then X2 is equals to minus half when U is an element of, and then we know that these two are always stable, but this one will be stable and unstable when we pass U is equal to 0. So let's try a diagram. This is where your cave sketching skills are needed. The square root of U just scaled by half. We will then just start from 0 and do this. This is X2 is equals plus half of root mu. All right, it's stable, so we are not worried. Then this one also does the same. And this is X3 is equals minus half root of mu. And we know here at X is equal to 0, that's where we have our what? Our bifurcation point. Bifurcation point. Okay, let's double our. All right. So then I will use the green color here. This is now X1. It is stable here, and then it becomes unstable when U is greater than 0. So you can see that it's a fork. The fork, the bifurcation diagram is actually a fork. So that's why it's called a pitchfork bifurcation. So this is X1 is equal to 0, stable and unstable here. So let's also now determine the direction of what? The trajectories depending on where you start on the bifurcation diagram. So we have two spaces where mu is greater than 0 and mu is less than 0. So all we will then identify is if we start our solutions here, they will be attracted to this. If we start the solutions here, they are expelled from from X1 but attracted to X2. If you also start solutions here, they actually repelled by X1 and attracted to X3. You start solutions here, they are attracted to X3. And in this space here, if you start solutions, they will always go to X1. And if you start solutions from below here, they will always go to X1. So this is pitchfork bifurcation. So I will draw a pitchfork bifurcation. It will be interesting if you can also, as an exercise, try to draw the bifurcation diagram for dx dt is equals to u plus, now this one would not work. Okay, it will be a 4x cubed minus 2x. This one. This is the one that can work. All right, and check what type of bifurcation it exhibits, which should be pitchfork, and draw the bifurcation.